Yeah, now I'm gonna record. Now I'm recording. Bear with me. You guys mind that we lost that bit? I'll try and repeat it a bit, right? So, I don't know. I just want to keep going. Is that all right? There won't be any sound for until now. Sorry about that. Anyway, so you'll say skip through to like minute 5 until, or I could start it again. You want me to start it again? No, just keep going. All right. So the one on the left has got a lot more detail than the one on the right. The one on the right is more abstract, right? The one on the left, some people might like that. You would like this map if you're doing cycling or hiking, you know, walking around, or maybe even driving your car. This map would be better because you can see some things, right? So, I mean, it's even got different shadings, which would represent different land use. So you can see, oh, well, here's an industrial area, here's a residential area, here's a park. All right, so that would be kind of useful. But what if you just wanted, all you want to do is you want to ride the train or metro? So then this map might be more appealing. It's more accessible because you don't have to sort through a lot of stuff, right? You just can look there and say, oh yeah, I want to go there. So I'll just do this. You know, I'll get on the train here and I'll go there. It's a lot quicker and easier because a lot of information is gone. We only have the information that we need. Abstract. Got the idea? Yeah, I think that shows it pretty nicely. And I'm sorry about not recording the other one. So here's another map of a tube or a metro. This one's Washington, D.C. It kind of looks like the tube or metro map that you'd see here in Qatar, but maybe a little bit bigger, few more stations. It's a big city. It's been around for a while. But some things are similar, and that's kind of cool, right? All tubes, metros have some similarities. So you came from Moscow or you came from Washington or London, you come to the Doha metro, you look at the map, you kind of understand how it works, right? Because it's kind of like the map you had at home. You have colors. You know that if you get on the train here and you don't get off, you're gonna end up here, right? But if you wanted to go here, then you'd have to stop, get off the train here and change trains and then go there. So, I mean, there's a lot of information in that, but there's a lot of information that's missing too, right? It's not showing you where the Capitol building is, and it's not showing, you know, all these things are in Washington. It's not showing you where the Supreme Court is. It's not showing you where the mall is. You know, it's not showing that. It just shows the stations, you know, because that's what you need to get around. Another map, if you were a trucker, this is a map of Virginia. If you're a trucker, this is the kind of map that would be useful to you because you'd know that if you want to get your 60-foot long truck around the corners on the roads, you want to stick to the big roads because the little roads, you know, you could have some problems with them, right? So you would look for these big roads with the bold colors and the big, what do you call that? Shields, the shield with the number on it. And you'd know if you're a trucker that if you see a road there that says like 95, that's an interstate highway. The interstate highways go all the way from one end of the United States to the other. So this one will go up to Maine and down to Florida. That's a 90. I don't know if you care about this. I don't know, but there's a lot of information in there, right? You just say, oh, 95. What's that mean? Anything that's got a 5 on the end of it, that means it's an interstate going north and south. Anything that's got a 0 on the end of it, that means it's an interstate. Oh, only if it's an interstate, right? If it's an interstate and it's got a 5 on the end, it means it's going north south. If it's an interstate, it's got a 0 on the end, it means it's going east west. Easy peasy, right? So here we got a 95 and an 85 splitting off because the 85 is going to go further west. If you're a truck driver, this would be very useful. It has information in it, but only enough for you as a truck driver. Now you're not a truck driver. You're looking at a map which is similar. It's got the same stuff in it. This is Virginia, but now our need is different, right? What our need is, I need to look at the map and see. I need to look at the map and see, do I need to wear a jacket today? Do I need to wear a raincoat? And I can look at the map and see that, right? Or maybe if I'm going to Richmond, nah, I don't need a raincoat. All right, so if I hang out in Virginia, I'm probably not going to need a raincoat. I don't know if you guys are familiar with Fahrenheit temperatures. There's like one country in the world that uses Fahrenheit temperatures. 80 is about 26 degrees Celsius. Information abstraction. So maps. We've been looking at a couple of maps. A map represents some physical reality. It's an abstraction of a physical reality. Now, a map's going to be physical, but it's a physical abstraction of a physical reality. We have other abstractions, information abstractions of physical things. So we can do an abstraction of people that are at the college. And there's different classes of people, right? There's students and there's teachers and there's administrative staff. And there's different kinds of things that we need to know about them. So each of those different classes of people we would store different things about them, I suppose. Well, so for students, we'd have to have some way of storing all of their courses and their grades, because that's kind of important for them. They want to have a piece of paper that says, I did these courses and I got these grades. For teachers, we like to get paid, right? So there'd have to be some way of storing, what is their salary and, when do they get paid and how much? Those kind of things. So different classes of others, but there's some things about teachers and students that are the same. Like every teacher has a name, every teacher has an ID, every student has a name, and every student has an ID. There's lots of other stuff that we store in our computer systems here besides just that. We also store information about all the rooms and all the courses. And so, for example, we're in this room here. Nobody else is knocking on the door trying to get in, because this room is only for this class at this time. Nobody's going to try and come in here, because we got a system which says Mark Floden is in this room today, right now, and all of these students are in here with him, and they're doing this course. And other courses are happening in other rooms. And yeah. So, I mean, that concept, I'm sure you're familiar with. That's the only way that you can get airplanes to work as well, which is even more tricky, right? Get the right person in the right seat. So supposing we were going to store some information about movies. So we could say a movie is an entity, or movies, the class of things called movies, is an entity. And then, then each movie, we would record certain things about it. What are the things that we would record about it? These are the properties. Movies have properties. They have titles. They were released at some year. They have a length of time in minutes. They have a genre. They have a format, and they have a price. Now, notice here we've got in brackets the types of the data. So this would represent a table in a relational database. A relational database would be something like SQL. So you'll be working with something that within a year, I would say, you'll be doing a relational database course. You'll be creating a relational database. Maybe you'll even install a server on your own computers, or you'll use a server here at the college, and you'll be creating databases. You'll be using web pages to interface with your, and so you'll be using PHP and HTML and JavaScript, and you'll have these cool little apps that kind of look like Amazon or something like that. You'll be doing all that kind of stuff in the next couple of years, but behind it, what makes it work is going to be SQL tables that are storing your data. And so before you can do that, you'll have to analyze the data. Okay, what in my system, what are the things, what are the different entities that I need to store data about? Then what are the relationships between the entities? Okay, and then what are the properties of those entities? And from that, you'll be able to develop your tables in SQL, and then you'll be able to store your data in it, and you'll have a live system. Live system. Sometimes people call it SQL, structured query language. It was invented in like 1982. So as opposed to the previous database systems before 1982, before SQL, were network database systems. They were really kind of hard to work with. Network and hierarchical database systems. You had to be a programmer to sort of use them. You have to be a programmer to use HTML, but the programming is much easier. I mean, you just select this from that. It's really nice. SQL is definitely powering the internet for us. I mean, we have web servers and SQL servers that are combined. Probably, I'd say yes.
The price is like how much it costs, like $15.
It could be. So usually there's a difference between price and cost. Price is what you sell it for. Cost is how much you paid for it. So, all right, in this case, we only have one, which is, yeah, it's a sales price, right? How much you can sell.
Gone with the wind, very high price. I tell you what, because no one has it. It's rare. You can't
It's,
find it anywhere.
yeah, I don't know if it's copyright anymore because it's like 1937 already. I've seen it many times.
You've seen John Wayne?
I thought you said Gone with the Wind.
No, Gone with the Wind. I said it, but it's who watches 1910?
Yeah, I've seen John Wayne.
The last thing I watched was The Godfather, 1971.
That's not John Wayne.
No,
Godfather, that's
the oldest thing I've watched.
all right. Yeah. Godfather's good.
It's your age, right?
Yeah, The Godfather, Goodfellas, Donnie Brasco, Sopranos. Yeah, you like gangster movies. Yeah, they're fun. All right. You like Westerns because of Johnny, what is he again? John Wayne?
John Wayne.
Yeah, Westerns. I like Westerns. Layering abstractions. So the idea is the more you abstract, every time you abstract, it's like putting a layer on, and the layer is making it so that things that you could see before, some of those things you can't see, and only some things you can see. So you're putting each layer is like a filter. If you get enough stuff on there, then there's hardly anything left to see. So imagine that map that they had of Rotherham, which had a lot of detail on it, and then look at the map of the tube. And yeah, Omar, you're distracting some students. So when we got to the more abstracted one, that was by putting more layers on. That was the thing. That's what we mean by this. You can peel back a layer, remove a layer, and then you can see stuff that had been abstracted away. So abstracting is a process of removing information to make it more accessible, to make it so easier. Okay, so we're talking about movies and abstraction. I was watching a movie last night, and it was about this lawyer, and he was suing a big chemical company. It was a Dow Chemical Company. Dow Chemical Company made the compound called Teflon, which is used on, you see that movie, right? Which is used on, I don't know, it was on Netflix, I think. But it's used on fry pans and things like that, so things don't stick to them. It's a really nice chemical. And it's non-reactive, so it's kind of safe. But the precursor molecules, that is the chemicals that you combine to make Teflon, one of those is this thing called C8. And what was happening was the Dow Chemical Company, this C8 was escaping from its place where it was supposed to be and turned out to be quite bad. I mean, at very low concentrations, it was causing people to have deformities when they had, women who had pregnancies would have babies that were deformed. People were getting all kinds of cancers. And yeah, it's just a really, really bad thing, right? And so one of these sick people who's dying of cancer goes and gets this lawyer to help him. And the lawyer goes to sue Dow. And the court says Dow has to release all of its information that it has about C8. And so what does Dow do? Dow sends him, they got a room that's as big as this, it's just full of paper. And they send this one lawyer all of this paper. And yeah, now, so what he needed was some abstraction, right? Because that's not useful. It's just too much information. I mean, that's the idea. If you got a room full of papers, what are you going to do with it? It's actually much better for you if you can just get the information that you need. And actually, the guy just worked really hard, and he was able to get the information out of there. Sorry? I can't remember what it was called. Yeah. Sorry? Who? No. I don't think so. Anyways, you get the idea, I hope. Abstraction. If you got too much information, it's not too useful for you. A lot of the things that we do in computing is taking information, which is a lot of information, sort it out and make it useful. And as I mentioned a minute ago, that's what accountants do, right? Accountants make information systems to give information which is useful to managers to make decisions. If it's not useful, why do it? And we know it's useful because we're prepared to pay for it, right? We're prepared to pay for computer systems to get this abstracted data. All right, so on the left and the right, we have two representations of the same system. What's happening in this system, which is represented in two different ways, is that somebody is sending an email. Now, on the left, we have a much more abstract representation. This is a representation which is accessible. Anybody could look at that, I hope, and just by looking at it would know what's going on, right? We're going to open an email application. We're going to write an email. The email is going to be stored into computer memory, and then the computer memory is going to transfer that email to the network. That's what it says, right? From that, you know what it means. What about this? All right, so if you're a computer hardware person, if you finish your first year at this college and you've done the INFT 1101 and 1201, you'll know what this is. All right, so we've got a user interface on our application. So this is saying here's an email application. Oh, this is what it looks like. Then we've got representation of the data. Data is in the computer is only zeros and ones, right? So it's going to be like that. So that's our data. And then we've got that data put onto the network. And on the network, the data is just cycles of 5 volts and 0 volts, 5 volts, 0 volts. Okay, 0 volts, 5 volts, 0 volts, 5 volts. The 0 volts means 0, and the 5 volts means 1. And so that's how we do it. We can put all this information by very quickly or somehow doing some multiplexing to get lots and lots of 0 volts, 5 volts going on our copper wire so that we can send information from one place to another. Now, if you're not a computer person, you don't care about this. You don't care about the 0 volts and 5 volts, right? You're just the manager, right? What you want to know is my email, is going to go into the computer and then go on the network. But if you're a computing person, you're going to have less abstraction, right? So the abstraction is different in each of those, right? So different layers of abstraction. I hope that makes sense. Whizzing along. Again, now we have 2 different objects here, but they're related. This would be something that you'd see in a car rental company. Car rental company rents cars, motorcycles, trucks, and vans. Now, all the vehicles have certain information about them, which is stored in the system. So we've created an object called vehicle. Now, I say object because this is the object-oriented programming. Object-oriented programming, you will learn a lot about. When you start programming in Python, it's an object-oriented programming language. You might use Java. It's also an object-oriented programming language. You'll need to learn about that. You don't need to know it for this course. It's just there. So you know what I mean? What we're doing at the moment is we sort of drop some things that hopefully there's a hook in your mind. And then when you come to that class, oh, that's what they meant. Object-oriented. Yeah, I remember somebody said something about that once. Can't remember what it was, but yeah, it was something about a van and a van and a vehicle, right? So in object-oriented languages, we have objects. Objects can have relationships between them. Objects can be like parents and child. And so you can have this hereditary idea. So we can have a situation where van is a child of a vehicle class. And so all of the properties of a vehicle are inherited by the van. Does that make sense? So because it's in that family, I guess you could say. So we don't have to say, so we create a little object for the van, but it has inheritance from the vehicle, and all of those properties come to the van. We don't have to record them in this object here. Omar.
No, the vehicle doesn't need storage capacity.
No, because we have a new object for van, and it's only in vans that we care about the storage capacity, I guess. I mean, you might argue that that's not logical. I don't know. I mean, I guess we're assuming that rental cars, people don't take a lot of stuff in them. If they want to take a lot of stuff, they get a van. That's what we're assuming. So the problem with abstraction is we can abstract too far. So supposing going back to that model that we saw of the Rotherham tube, supposing somebody wanted to look at that map and they decided that they wanted to do some hiking. It's not going to help them, right? We need to peel back so that we can see where the river was, where the streets were, and where the different things were in there. So we can go too far. When we've gone too far, then we're going to have to peel it back, unabstract, and we can call that leaking. We're going to leak some data. Well, you could also refer to that. Also relates to, I suppose, the van and the vehicle. What we did to solve the problem of the leaking you know, we had vehicles and then we realized, oh, we got some vehicles that we have to record the storage capacity. Oh, well, what we end up doing is creating a new object, which is van, where we store the storage capacity. But it could be that all of the vehicles we're interested in their brake pads for maintenance. And I'm sorry about this because I'm sure that there's somebody in the class that knows that that's not how you spell braking, nor that. That was how you spell braking, but that's how you spell braking when you break a stick. But when we're talking about braking, like stopping, you spell it like this, braking. Yeah. Car people know that. Motorbike people know that. Other people, maybe not. I don't know. All right, so modeling. We've talked about a few different models. We got models which are maps, got models which are model airplanes. We got models there that were the diagram that we used to show the email. We've had a few different models, and a model comes out of abstraction. A model represents something in the real world, but represents it in a simple way, which is easy to sort of work with. Okay, I think that I've said enough about that. Let's look the next one here. So here is a model of models. All right, so this is kind of recursive. Think about that word. You'll learn a lot more about recursive later. So as again, we're dropping things. You don't have to know recursive now, but you'll need to. Actually, last lecture in this course, we talk about recursive. The idea of recursive is when you have a module which calls itself. This is kind of recursive because we have a model which is about models, a model of models. All right, so this is an entity relationship model. And what it does is it tells us the relationship between two different entities. And the two different entities are model and reality. And the relationship between a model and reality is that a model represents reality, or reality is represented by a model. And then there's another relationship between them, which is the model hides some of the details of reality. It must be, otherwise, you know, it wouldn't be useful. I mean, it must be accessible. So there's two relationships between them. Those relationships are represented by those arrows. Yes, Omar.
Can you explain that using cars? Like this model of car has, you could say the whole model number. Yeah, but in reality, it's just called a port fusion. Is that what it means? All
right. So you would have a data model, like we saw a minute ago, which was like our data model of vehicles. In the data model, we only record the things that we need for our system. So in your system, yeah, you might record there the model of the car. I mean, people here refer to the model, often they're referring to the year of manufacture. But in other places, it's like, you know, okay, model is Patrol or FJ or Land Cruiser or something like that. So you would have all of those, all of the things that you think you need to record would go into a data model, which you would then use to design your table to store information about cars. So a car would be an entity, and you would model it as with properties. And each of those properties would be things like, yeah, it's year of manufacture, you know, how big is the engine, you know, how much does it cost? I mean, you know, whatever is important to you to put into your system.
The model is more complicated than reality.
It should be the other way around. The model should represent reality but in a way which is more accessible. So now let's not get confused here. When we're talking about cars, we're not talking about car model. We're talking about a data model which represents cars. And so a data model is just going to be it's going to go to a table, and the table is going to say, this is a car, and the car has these things. These are the things that we record about a car. We won't record everything about a car. Some things you don't need to record. You don't need to record that it has four wheels, because that's implicit by the fact that it's a car, right? Yeah. So, Hafsa.
Yeah, when we say hide some part of reality, how do we determine what part is to be hidden?
How do we determine which part is hidden?
Which part we need to hide and which needs to be included.
All right, so I guess the way to look at it would be to look at what needs to be included, and then you would hide everything else. That's the way I think about it, right? Just start with imagine that you hide everything, and then just sort of say, okay, well, actually, these things we need to know. So, for example, a student, there's a lot of information we could get about students, right? You know, height, age, weight, you know, all of these things. But, you know, what do we need in our computer system? We need to know their QID number, you know, maybe their birth date, because that goes with the QID. We need to know their grades from high school. You know, we don't need to know a lot of other stuff about them. You know, they've got brothers and sisters. I mean, maybe they're married, maybe they got kids. That doesn't really matter for us. I mean, you know, that's important in another system, but in our computer system, we would hide that. We just say, no, it's not going to affect their grade. So we were not going to record it. Does that make sense? That's the way I would look at it. All right. So entities, core concepts. What we're talking about here in the next few slides is this idea of entity relationship modeling. Entity relationship modeling is used for data analysis. Data analysis is used to design databases. So if you wanted to do a database, you would do an entity relationship modeling. And so you'd say, okay, here's all my entities. And between these entities, there are these relationships. The diagram just a minute ago between the model and the some part of reality with the arrows, that was a cut down entity relationship model. So you would be doing that. And in your entity relationship model, as the name suggests, we talk about relationships, which is how are the entities related between each other. And these are some of the ways they could be related. So A could be like belonging to B. A could contain B. E could be required before you do F. They could be in the same space. So there's a lot of other things that you could record. You would know from your business rules. And so basically, there's this whole idea of systems analysis, business analysis. And what you'll do is when you have the problem, you'll look at what are the business rules. You know, and as I said, you know, we're here at the college. We probably don't need to know that you've got a little sister that's 8 years old and goes to XYZ school. That's really important to you, but it doesn't affect our records. And so we're going to hide it. Does that make sense?
Sir, before you skip, when you say A belongs to B, is it reversible and you could say that B belongs to A at the same time?
I guess.
Like, will it work?
All right. If you look at the next one, C, there's one which is a subset of the other. So I guess, yeah, if you look at, so if you look, C contains D, so D would not contain C. But yeah, I suppose belongs to could go both directions. Yeah, why not? So some of these are unidirectional and some of them could be bidirectional, going both directions. I think belongs to, I think like when people get married, they refer to it that way, right? They belong to, right? The husband belongs to the wife and the wife belongs to the husband. I guess, right? Parents and children, sort of similar. It's too late for that. But parents and children, children think that their parents belong to them, and parents think that their children belong to them. Am I right? Now, I don't mean that in a sense of property, but just like, you know, that's my family, right? I mean, that's part of my identity. And that's what we're talking about here, right? Is identity. All right, so we have properties, we have types, and I hope you remember when we looked at that table of the movies. It had the each movie had a name and it had a year that it was released, etc. And each of those columns had a type under it. It said it was an integer or it was a string. Okay, that's what we mean by type. The type would be what is the data type that we use to store this? Any rules that affect that entity? All of these things will be recorded, including the behaviors as well. All right. Now, we have a slide that's coming up after this, which is of a turnstile, which will explain this better. So I'll get onto that in a second. But by the way, the notes at the bottom, the reason why I'm doing this like this is because I've been told that I can't give you the notes at the bottom. So I'm showing them to you, but I'm not giving them to you. Does that make sense? Mind you, if you looked at the video, you could sort of tease them out. Yeah, if you want to look at a video. So we have a definition of what states are, what transitions are, what events are, and what actions are. So states are descriptions of entities at specific point in time, specific points in time because the state will change. And so, for example, you could record that in a variable. And what is the value of that variable? Transitions, change in state. We'll see all of this in the next slide. And so, as I said, I can't give you this in written form, but you can see it here. And it's in the video. So you can look at it. Sorry? Yeah. And so here's some more. This is the turnstile. So the idea of the turnstile is it restricts your access to a place. So for example, you want to go on the metro, but you need to record your presence there and maybe pay money. It's hardly anything though, what I've been told, right? And so yeah, do you use a special card or something? You go and buy a special card from people and then you put it on this thing and then it lets you on. Is that right? And so what probably happens is there's this thing that looks like a triangle and it turns. That's what we mean by the turnstile, right? And so you put the money, it could be a coin, but I think most places actually use a card nowadays. And you probably could use your mobile phone, right? And then the clutch releases on the turnstile and you can go in. Now, if you're just standing outside, so this is the starting point here, this little black dot. If you're just standing outside the turnstile and you push, nothing will happen, all right? That's static. Nothing happens until you do an action. You have to, well, it says here insert coin, but I think you could replace that with insert your card or use your card. Then once that happens, the turnstile will open. So the state has changed. Here we got a state, which is locked. Now we got a state, which is open, all right? Locked, open, state has changed. Then what will happen is it's open and you go through, all right? When you go through, when you finish going through, it locks again. Right, and so then you're back to where you were. The only way you're going to go the next one is they'll have to put their card on it as well. So this is a dynamic system. The state is changing. Here's our two states. We've got a locked state, we've got an open state. The only way that we're going to get this to become open is by using a card or inserting a coin. Once it's open, if we push it, it'll go back to being closed. I hope that makes sense. Yeah, it's explained there too. That's a turnstile. All right, another useful model, a fellow by the name of Leonard Euler. I don't know. Prussian, which means he's from Germany, the north part of Germany. He's actually in Königsberg, which it says is now in Kaliningrad. Kaliningrad is part of what used to be the Soviet Union. So yeah, anyways, I don't know if you care about that, but it's on the Baltic Sea near Lithuania. And okay, so there's a little town called Königsberg. König means king, so king city, whatever. But the thing about this city is that it's divided into 4 different parts. The 4 different parts are hard to get to from each other because they're separated by canals and rivers. So if you're in this part, the only way you can get to this part is by going across a certain bridge.Maybe there's more than one bridge, but the only way, you can't just go across, right? You have to go across by the bridge. And so they asked Euler, they asked him if he could come up with the best way of visiting all of the 4 different places without going over the same bridge twice. It's kind of like the traveling salesman problem that we had in lesson 2 or something like that. It was lesson 1 or 2. We had the traveling salesman, had to visit a lot of different towns with using the least amount of gas. So it's kind of like that. But what he had to do is he had to visit each part of the town without going across the same bridge twice. And so Euler was kind of smart. He's looking at that and he says, you know what? That's got way too much information. I will abstract it down because he's a mathematician. Mathematicians abstract things, right? And so he said, well, what I'll do is I'll make this little map. Here's the North Bank. Here's the West Bank Island. Here's the East Island. And here's the South Bank. And so the whole of the city is represented by 4 different little ovals. And then for each bridge, for each way of crossing, he put a line, right? So there's 2 bridges, I guess, between the North Bank and the West Island. There's 2 bridges between the West Island and the South Bank, but there's only one of these other things. And what he had to do is now he's got an easier model, right? Now he could, so he was able to, looking at this is kind of hard to come on the answer, right?
Yeah.
But this way it's a lot easier because, and I think you could do that too. You're just gonna look at that, okay, I'm gonna go there, there, there. You'll find a way of doing it without going across the same bridge twice.
It's like the one on the metro station.
Yeah, it's abstract. He made it a lot more abstract. Another abstract, and again, there's a lot of notes on there, so you might want to look at that on the video if you're interested. But the climate models is very much abstracting. There's so much information about the climate. Now, so what they got is they got a lot of information, which is historical information. What have been the temperatures in different places around the world over the last 100 years, 200 years, whatever. So they got that information. They got other information that they use, which is what is the concentration of carbon dioxide in the atmosphere at different levels and at different times and at different places. What is the concentration of methane gas in the atmosphere at different levels at different times? And what is the acidity of the ocean? Because that's a measure of the carbon dioxide that's dissolved in the water. So what is the pH of the ocean at different places at different times? And using all of that, you can make a model which is going to be very mathematical. So what they'll do is they'll test their model. They'll look at all the data that they've got for the last 100 years, and they'll say, I think this equation fits that. Oh, and no, it doesn't. Okay, we better change it here and change it there. Now, I think this equation fits that. And eventually they get an equation that sort of says that, look, over the last 100 years, these temperatures changed in these places, these carbon dioxides changed in these places, these ocean acidity changed in these places, and my model works. It shows that from 1900 till now, this would happen with those things. And so now that we have a model, we can say, okay, now we can do hypotheticals. We can say, well, what would happen if the concentration of carbon dioxide increased by so many parts per million in the next 50 years? And that's where we've got all this stuff. And you may have heard of like Greta Thunberg. She's not a scientist. I don't know why I mentioned her, but there's a lot of scientists and meteorologists that sort of talk about this, and they got a little bit of alarmed, and they said, well, you know what, the temperature is going to rise by 1 degree in 100 years or something like that. That's kind of bad. Anyways, they did it from models like that. You can read about that. That's kind of fun, I suppose. All right, so almost finishing off. The last slide. I don't like the last slide, but we're in the last two slides. This slide I like. This slide gives us the concept of cardinality. Cardinality is what is the relationship between a property and an entity? Is the relationship a one-to-one relationship, or is it a one-to-many relationship? So if it's a one-to-one relationship and we're doing data modeling, then we can say that that all belongs to one table. We can create a table for that in our SQL database. And so that's what they'll do. So they'll say, can I make a table called student? Yeah, okay, so what would I put in that student? Everything that's one-to-one to student. So when I say one-to-one, it's not 0-to-1. It must, and it's not 3-to-1. It must be 1-to-1. So for example, every student has one date of birth, right? They don't have 0 date of birth and they don't have 3 date of birth. They got 1. So that's a one-to-one relationship. So we can say that in our student table, we're going to put date of birth. Every student has a name, and it's kind of a one-to-one on that. Every student lives in one place. And so there's all of those are one-to-one. However, according to this model, students have 3 phones. Is that true? I don't know. But if students had 3 phones, we couldn't record the phone as part of the student table. What we would have to do is we'd say, oh, that's a one-to-many relationship. One-to-many relationships can't exist in the same table. We'll have to create a new table. And so that's what you do. I agree with you on that. Some people, you might have I don't know. Maybe you could put the forename, you could have a concatenated forename or something. And the last one, last model. So we've got a model there of a transaction, which is somebody orders something and they get it. So I guess this is like Amazon or something. You order something, you pay for it on your credit card, and after you've paid for it, eventually they send it to you. But there's a lot of steps on the way, and these steps, we see the relationship there of one thing has to happen before the next one. So we see that you're not going to get your item delivered to you until you've done all of these things. And probably these things here are not going to happen until you paid, right? You pay, And then once they've got the payment information, they're going to get from you, when do you want to have it, where you're going to deliver it, what time, and then eventually that's going to come to you. I think I'm kind of done. All right.
I have two questions.
All right.
One, this thing, okay, the previous slide, what was that? Like, was that the example of a database or?
I would say this is relational database modeling.
So in every relational database modeling, we can't have more than one thing for an element.
The entity has a one-to-one relationship with all of its properties.
It can't have more than one.
Yeah, you separate it out as a new table, a new relationship.
Why?
Because of this thing that we call redundancy. So if we had 3 things there, it'd be possible for you to enter it 3 different ways, and then you could get errors, or you could update it at one point, and you know, you needed to update all 3 and you only updated 1. So because of that, this problem that we call redundancy, we have to have our tables what we call normalized. So we have this concept of normalized relational tables. You can read books on this if you're interested. So we say that when we have a database, we like to get it to what's called third normal form. So to get it to third normal form, we go through first normal form, second normal form, third normal form. But in third normal form, there's no many-to-one relationships.
And how does this all tie into computer programming?
We use databases to hold our data in our computer programs. So no, SQL. So Access is the Microsoft. It's not running on a server. Access you can use on your Microsoft machine to do. It's quite powerful, and you can give it SQL commands. So when you're using Access, you're pretending to use SQL. But so what's happening nowadays is people are doing everything on the net, and so you need to have a server. And so your servers are going to must be server software, client server software like SQL. And so we actually have this thing that we call we use a bunch of tools together, not just one tool. We use a bunch of tools together. So we have we call them stacks of tools. You have a LAMP stack and a WAMP stack and a MAMP stack. I'll just briefly explain that, right? So your LAMP stack, that's using Linux as an operating system, all right? It's using Apache to sort of communicate between the servers, all right? It's using Apache, like an Indian, Apache. And then it's using MySQL, it's using the P is PHP. So the important thing about the LAMP stack is all of those tools are free. They're open source. So people like to use the LAMP stack because you can go and develop big systems just with all this free software. Or you could use a Windows version of it, which we call WAMP. And so it's using the Windows operating system, but all the other stuff is free. Or you can use a Macintosh version of it. A Mac version of it. And so that's the MAMP. But I mean, all those tools are free. People use it. You could sit at home and do a nice development. You can install a server on your laptop. And so you can run a little thing. But then, you know, to make it work in the real world, you actually have to have somebody host it for you. So you need a hosting service. So somebody to give you a URL so that other people can get in and so you can run things off your server. So you'll be doing that before you finish this degree. You'll be using all of those tools. Probably the LAMP stack. Well, I don't know. I don't know if you use Linux. I think so. I think you guys have to do an operating system course and you have to learn how to do Linux. And yeah, so when you're doing Linux, you've got shortcut ways that you can do things with the database. So you can, yeah, pretty good. You can install the database with your Linux, etc. Too much fun. Anyways, did I answer your question? I don't know, because at the moment I'm just talking.
You know, I forgot my question, but you spoke a lot, so I congratulate you for that. And I'll tell you one thing. Macintosh is a chocolate.
Is it what? I'm gonna end the lesson now. Is that okay with you guys?